My goal is to increase the voltage at the output compared to the voltage available on the power supply. Hi there, I'm back again. As usual, I received a lot of negative comments, but I have got a good question and someone pointed out to me the ECAT technology. First, the question. This guy had all 25 patents. Why is not a billionaire? It seems that on YouTube, nobody knows how we work in a company with patents. So let me explain. I think this is the same thing everywhere. When you work for a company, you have to sign a contract. This contract establishes how the individual property, the other name of patents, is shared between you and the company. In my contract, I agreed to transfer all my rights to the company because they paid a lot of money to maintain the patent, around 30,000 euro each year for a single patent. I received a small fee for every patent I produced, subject to its acceptance. If another company needs one of my patents, they will pay my company to acquire the right to make products. If a product is associated with my patent, only 2 patents were really used to produce equipment, I will receive a very small amount of money for each product sold, not millions. Another example of the interest of patents: if you are sued by another company pretending that you violate their patent, it is not unusual to compare the number of patents that you and the other company own. So it's very important to be able to produce a larger number of patents in a patent dispute. Someone pointed out the ECAT technology. This ECAT technology was invented by an Italian guy named Andrea Rossi. His invention was supposed to be associated with so-called cold fusion. So he got a lot of money from investors, but it was a fraud. But now he got arrested and is facing a lawsuit that can drive him to jail. This is not his first scam. He seems to be a serial scammer. And guess what equipment he tried to demonstrate with his technology? An electrical vehicle, a small Twizy car from Renault. He failed and the scam was discovered. So now let's go to the main topic of my talk. I will try to explain how everybody uses MOSFETs in the switching mode because I saw a lot of nonsense in YouTube. At the end, there will be a quiz, and the first African follower that provides the right answers will receive the gift from me, containing a set of components to play with MOSFETs and an Arduino Nano for the fun. The prize is only for people from Africa. I will send it to Chris and he will distribute it to you. First, let's take a look at the equipment used for the training. Slide 1. You can easily recognize an oscilloscope and the signal generator from a Chinese company. The oscilloscope possesses an internal equivalent of a multimeter, so using cursors or the software of the device, you can make measurements of voltage, timing, frequencies, power spectrum densities, and so on. It is not capable of measuring current. To do so, you need to acquire a very costly probe that can cost up to 4,000 euros to be able to make such measurement. The device has its own simple generator to calibrate 1 kHz square wave. You can see a screenshot of the recording on the right. About the generator, it can produce a great number of waveform signals: sinusoidal, square waves, triangles, noise, ECG signal, and so on. And you can also enter your own signal point by point. You are able to select the frequency up to 25 MHz for my generator, change the amplitude, the offset, the rising and falling time, etc. It is very convenient for experimentation. Slide 2. No need to explain the FLUC multimeter. It's a high quality multimeter but a little bit expensive. The thermal imager is very pleasant to measure the temperature of the component and also to check thermal problem in my home, like bad thermal isolation. Remember, I live in a cold country. You will see screenshots, pictures of temperature measurements. The LCR meter is a kind of multimeter with an internal sinusoidal generator that can be used to get information about components like resistors, capacitors, coils. It gives you the main and the parasitic parameters of a component. Let me recall that in the real life there is no perfect component. Every capacitor possesses an internal tiny resistor and an internal equivalent inductance. Slide 3. I just add the internal resistance tester. As its name suggests, you can measure the voltage of a power supply and its equivalent serial resistor. You can see here an example with a primary battery. Slide 4. I acquire on AliExpress these modules. One is dedicated for voltage calibration tests and the other for resistors and capacitors. Slide 5. Here is an example of calibration of the multimeter and then the measurement of the resistance that we will use on the breadboard. Slide 6. We go on with the coil measurement, showing the parasitic serial resistor, the diode measurement, and the load resistor measurement. Slide 7. As explained, the oscilloscope is not able to make measurements of current signal, so we need a way to get this valuable information. I acquired a small module to do that kind of things. The integrated circuit will transform the flowing current into a voltage that can be acquired with a multimeter or by the oscilloscope. The device introduces a small resistor in series with other components because there is a small magnetic sensor inside and a PCB track that produces a magnetic field. See the datasheet for more information. But this device needs to be calibrated. So with a regulated power supply, 30 volt 5 amps, and 2 power resistors, you can produce a fixed current in the range of 1 ampere and see what's going on with the device. As the device is able to measure positive and negative currents, the designers have introduced an offset at the output, so zero current will be in the middle of the output range, around 2.5 volts here. Slide 8. By the process of current probe calibration, you can get a crucial coefficient, the ratio between the output voltage change for a current change. Here we got 160 milliamps per millivolts per ampere. It means that for a current, for example, of 2 amps, you will get 120 millivolts of voltage deviation. Slide 9. To design an electric circuit, I use a simulator. I choose this one because it's provided by analog devices. It is called LTspice. You can study complex schematic like in the example of a conductimeter that I taught to Vietnamese students and build with them in practical classes. Slide 10. This slide is to give you an overview of the properties of the LTspice simulator. Take care that the simulation time can be very long for a complicated circuit, and when you ask for long time analysis with high frequency signals. There is no magic in the software, only mathematics, matrix computation, and computer science to get high precision simulation. If you need a very accurate simulation, don't forget to introduce the parasitic parameters of your components and to properly handle the power supply properties. It is a very valuable tool because you can change the values of your components, resistors, capacitors, coil, transistors, MOSFETs, without the need to go to your local electronic dealer. I give you here the location of the internet where you can download the simulator. Slide 11. The MOSFET in switching mode can be seen as a push button. Let me explain this analogy. When you push a button, the pins of the button are now in short circuit state compared to when the button was released. This is perfectly equivalent for a MOSFET. When you drive the gate voltage pin to a proper voltage compared to the source voltage, the conductivity between the drain pin and the source pin changes dramatically, switching from open circuits to nearly short circuits. This is not a perfect short circuit. There will be always a residual resistor between drain and source, but it can be very low, down to few milliohms for high power MOSFETs. The open circuit is also imperfect. There will always be a small current flowing in the device, but in the range of micro to nano amps. Slide 12. The first experiment schematics presented in this slide is just how to use a MOSFET to drive current into a pure resistive load. I introduced a small resistor in series of the load to mimic the current measurement probe. I have chosen the easily available RFR520 MOSFET. It can handle 100 volts and a large current, but not both at the same time. See the datasheet for more information. Slide 13. This slide shows only the applied voltage on the gate of the MOSFET with LTspice simulator and compares it to the waveform recorded on the oscilloscope. So everything is fine here. On the generator, I selected a frequency of 5 kHz. You can see in the figure a period of 200 microseconds, a voltage of 9 volts to drive the gate, and a duty cycle of 40%. Just let me remember that the duty cycle is a ratio between the time of when the signal is on compared to the full period. Slide 14. As the simulator is able to show you the voltage on every node of the schematics and to present the current flowing in every branches, I show you the current that the load resistor is expected to carry. The maximum current is when the MOSFET switch to its own state and can be easily approximated without the help of the emulator by a raw computation. In the off state, the current is practically zero as expected. Slide 15. This is a breadboard populated with all components. You recognize the MOSFET, the load resistor of 56 ohm, and the current measurement probe. There is also a 25 kilo ohm resistor between the gate and the ground. In the quiz, I will ask you a question about the function of this resistor. You can also see the power supply wires with a diameter larger than the usual wires used on my breadboard. Slide 16. Let's now go to the heart of the matter. My goal is to increase the voltage at the output compared to the voltage available on the power supply. How can we do that? The idea is fairly simple. Everybody knows that when you interrupt the current flowing in a coil, an opposite high voltage is produced. So, with the help of the MOSFET, I will regularly switch on and off the current in the coil, So pulses of high voltage will be generated at a constant rate, here 5 kHz. The next step is to capture these voltage pulses to properly charge a capacitor. To avoid the discharge of the capacitor when the drain voltage is low, I will use a diode, so the charging current will run just in one way. The only way to discharge the capacitor is by the current flowing into the load. The diode is a special type, Schottky diode, with high speed and low dropout properties. And the model is incorporated in LTspice. The same for the coil with a series resistor included. There is no magic in the design. We just store energy in the coil in the form of a magnetic field and then allow this energy to be released to the external circuits. So let's take a look at the way everything works. Slide 17. I use the simulator to help in the design process, but also to be able to predict how the circuit works. So take a look at the simulation of the output voltage with a high value resistor. Compared to the observation which gives us a voltage of 31 volts, the simulator clearly failed to predict the output level. It took me several minutes to obtain the LTspice results on a powerful computer. And it seems that the output voltage will continue to increase with an exponential shape. Let just me point out that in this case the output power is very low, in the range of tenths of milliwatts. Remember that the power supply is only 3 volts. Let's change now the load resistor and see what happened. Slide 18. The load resistor is now only 56 ohms. And you can clearly see that the simulator correctly predicts what we can observe on the board. The output voltage stabilized in a few seconds to a little less than 10 volts. The prediction error is less than 5%, which is fine for me. Let's take a look now at the current prediction. Slide 19. You can see in the simulation on the recorded output of the current probe, the shape of the current flowing in the coil. Both shapes are the same, and the magnitude of the maximum current differ by less than 10%. You observe some noise on the recording that is not present on the simulation. This is always the case, except when you introduce yourself noise signals in your simulation. But the level of noise is indeed very small and can be filtered. Don't forget to use a power supply capable of delivering at least 6 amps under 3 volts. Slide 20. In order to be able to compute the yield, which is simply the ratio between power delivered to the load and mean power extracted from the power supply, we just need to remember the voltage at the load and estimate the integral of the current wave from a single period of 200 microseconds. Taking into account the maximum current on the same period, here you can see the computation leading to a measurement yield of 50%. Slide 21. It is now crucial to examine the power losses in all the components, both passives and actives. LTspice has a dedicated command for this purpose. The cursor turns into a thermometer, and you can place above each component to see how the power is produced or delivered. It is very important to see that the power evolves according to time. So the right thing to do is to compute mean power, not instantaneous power. LTspice possesses such capacity to simplify your computation and is used here to extract valuable information. Slide 22. Now we can also estimate the mean power provided by the power supply and the power delivered to our resistor. The power delivered to the load is constant because of a constant voltage available on the capacitor, but if you zoom in, you will see small voltage ripples. Note here that the power extracted from the power supply is negative. This is a convention that LTspice uses for a power source where the current comes out of the component. Slide 23. Just observe the temperature reached by the MOSFET with a thinner load and with a medium load. Slide 24. Now the most important part of the talk, the power balance. I computed the power on all the components of the circuits. As we demonstrate that simulator is able to predict current in the branches and voltage on the nodes, you can trust it to approximate the power balance as shown here. The final simulation yield, which is simply the ratio between the power delivered to the load and the power provided by the power supply, is a modest 57%. It is far less than modern integrated circuits that can go up to 95% or more. You can compare this yield with the measurement yield, which is only 50%. You can also play with the simulator to challenge my design. Slide 25. Now we're able to compare the power balance within the simulation and the same measurements parameter. 16% of error between both estimation and which is acceptable for such a circuit. Sorry for this error. On slide 26, the only main conclusion is that MOSFETs cannot produce power as a switch. They only dissipate power, so you usually need to attach these devices to a large heat sink to cool it down. There is a very low power introduced by the generator, less than 7 milliwatts. In other form, the output power is always less than the input power. The LTspice has some limitation, but it can be used to redesign a large set of circuits. The output changes according to the load resistor. This is the reason why, for an effective design, a closed loop is needed to be introduced to maintain the output at a constant level. This is the way modern DC converter works. My yield is modest and depends on the output power, so it needs to be improved by a clever design. Slide 27. Take a look at the components you will receive if you succeed, because I teach this application to my students. I bought a lot of components and I have spare parts also. It is not a problem for me to collect a small number of pieces for you. Slide 28. First question. In the datasheet, you can see that the MOSFET we used can handle a constant current of 9.7 amps and up to 38 amps for a pulse current. Can you explain why? Second question. What would be the effect of a power supply with a great internal resistance on the voltage supply to the circuit? Third question. What parameters limit the maximum current level observed flowing in the coil? Can you improve this maximum without changing the power supply level of 3 volts? And the last one, more difficult. What is the function of the 12 kilo ohms resistor between the gate and the ground? I hope you enjoy the presentation. As usual, I'm open for discussion. As we are purely in a technical field, please stay in the same topic and provide example. You can also play with LTspice and find a better design than mine. My conclusion is when you use MOSFETs to make high voltage, don't be confused by the volume of this voltage, particularly when the output load is a high resistor, which translates to very low power at the output. If you are not convinced, I recommend you to take a look at the website of integrated circuit providers like Texas Instruments and Analog Devices. It's much better than YouTube because hundreds of engineers are working in the field. But see particularly application notes. You will find valuable information about the losses in DC to DC converter, step up and step down. Remember that with such device, output power is always less than input power. Finally, as the talk was for educational purpose, feel free to copy and distribute the slides. If you are kind, you can just give me the credit for the work. As I am a great fan of Bob Marley, and I have the chance to attend his concert a long time ago in France, the show was marvelous, and I will remember it for the rest of my life. So let me offer you a glimpse at the famous song Africa United. I also attended a concert of Jimmy Cliff, also a great artist. Thank you for your attention. Hasta luego.